Yeah. All of you are done writing the question. Please let me know. Yeah. So all of you are done writing the question. Yes or no? Please raise your hand. Okay, fine. So most of you are done. Okay, most of you are done. Now, please look at this solid that is Ni 0.98 and oxygen is 1.00. Okay. So what does that mean? So if I extrapolate this, that means for 100 oxygen, we have 98 nickel. Yes or no? Tell me. This is the meaning now. Can you understand the meaning, all of you? हाँ ना जल्दी बोलिए. Yes or no? Yes na? Okay, fine. Now, in reality, the ideal nickel oxide, the ideal one should have a formula, a chemical formula, which is nickel and oxygen, nickel oxide, like this, simple, 1:1. The ratio, ideal ratio is 1:1, and here the ratio is 1:0.98, right? This is the ratio here, and the ideal should be 1:1. Now, this type of solid, these are known as non-stoichiometric solids, okay? So, if you look at here, then I've written the definition that ratio of the compounds in which the ratio of positive and negative ions, right? Positive and negative ions present in the compound differs from the required by ideal chemical formula. And these are known as non-stoichiometric compounds, and the defect is known as non-stoichiometric defects. Now, let us look at this question, what it is saying, and what we have to find in this question. First thing that I will do is that, I will say that in 100 oxygen, or rather I should say for 100 oxygen ions, there will be 98 nickel ions. Okay, there will be 98 nickel ions. This is the first thing that I will say. But still, the magnitude of positive charge should be equal to the magnitude of negative charge. Why? Because it is not giving me any charge here. This is neutral, right? We don't have any charge in this particular solid, in this particular molecular compound. That is why the magnitude of positive charge should be equal to the magnitude of negative charge. Is that correct? Yes or no? Please tell me. Is that correct?
Yes, sir.
Okay. So let us now calculate the magnitude of negative charge. This magnitude of negative charge will be, so magnitude of negative charge. This will be only due to oxygen. And we know that in nickel oxide, they have said that the nickel is present in Ni2 plus also. And it is also present, some Ni3 plus is also present. But when we have oxygen, this whole oxygen will be hot, oxygen 2 negative only, because this is the only oxidation state of oxygen, that is O2 negative. So magnitude of negative charge will be what? So we are taking 100 oxygen ions. That means we have 100 into the charge on the magnitude of oxygen. The magnitude of charge in oxygen, how much? It is 2. The magnitude is 2. The charge is -2. But please remember, we are talking about the magnitude. We're talking about the magnitude. That means the magnitude of positive and negative should be equal. If there are 200 positive, there should be 200 negative also, right? So magnitude of negative charge will be equal to 200. I am not writing the sign for charge because we are only interested in the magnitude. Now let us look at the magnitude of positive charge. For that, we need the number of Ni2 plus and the number of Ni3 plus. So what should I take? I will say that let us take the Ni2 plus as x. So how many Ni3 plus will be there? So we know that there are total 98. So Ni3 plus will be 98 minus x. Is that clear? Yes or no? Please tell me. Is this clear?
Yes.
And I am taking Ni2 plus as x, and Ni3 plus will be 98 minus x. So magnitude of positive charge will be equal to, now this X will have two positive charge. So there will be two positive charge for each X, plus there will be three positive charge for each 98 minus X atoms or ions. So what will be this equal to? This will be equal to 2X plus 98 threes are 300 minus 6, which is 294 minus 3X, right? So this is the magnitude of the positive charge. This is the magnitude of negative charge. Now they should be equal. That is why 2X plus 294 minus 3X should be equal to 200. Now what I'm going to do, I'm going to put the 200 here and I'm going to make the variables X and 3 go there. Okay, so this will be equal to, so 3X minus 2X will be equal to X, and this will be equal to 2, it will be equal to 94. Okay, so if you solve this, X will be equal to 94 and 98 minus X will be equal to 4. 98 minus X will be equal to 4. So we have, this is the number of Ni2 plus ions. So they're asking here is the fraction. So fraction of Ni2 plus is equal to the number of Ni2 plus ions, that is 94, divided by the total number of Ni ions, that is equal to 98, and the fraction of Ni3 plus, this will be equal to 4 upon 98. So please write this down. Let me know when you're done.
So do we need to simplify the fractions?
You can simplify. It's okay, but okay. You can. Please let me know when you're done. Okay, 3 students are done. Shravya, Atif, Pinashi, waiting for others. Abdul Rahman, Ania. All of you got understood this question? Yes or no? Please tell me.
Yes, sir.
Okay, electrical neutrality is the main thing that you have to consider in this question. Okay, magnitude of positive should be equal to magnitude of negative charge. Waiting for Abdul Rahman, Huzaifa, and Mohammed Saif. Please write this down. Let me know when you're okay. Huzaifa and okay. Abdul Rahman, एक और चीज है. Like, why do you leave when I'm asking the Viva? Abdul Rahman, can you please turn the mic on and tell me? Yes, Abdul Rahman. Okay. Abdul Rahman, please tell me now, like at least write in chat something. I can see you are here. And this is not good, Abdul Rahman, okay? Okay, fine. All of you can lower your hand. Okay. So we have non-stoichiometric defect, and now we are going to classify the non-stoichiometric defect into two parts. Acha. Now, in this case, can you tell me which is more? We have anions more or cations more? In this question, what do we have? Which are more, cations or anions? Which are larger in number?
Anions.
Anions are larger in number, right? That means we have less number of metal. Correct? We have less
Yes.
number of metal. So this is one type in which you have less number of metals, and there is another type in which you have a greater number of metals than the anions. Okay, so there are two types: metal excess defects, in which you have more number of metals, and there is one which is known as the metal deficiency defects. Okay, now in metal excess defect we can create excess of metals by two types. We can either remove anions, or what we can do, we can add cations. Right, so anionic vacancies will be there if I remove an ion, and if I add cation, then what will be there? There will be cations in the interstitial site. For metal deficiency, what we can do, we can remove cation, and what we can do, we can add anion. So these are the two things that we can do. If I remove cation, then there will be a cationic vacancy, and if I add anion, there will be a presence of extra anion in the interstitial site. So let us first of all look at the anionic vacancies. Okay, so metal excess defect due to anionic vacancies. So what is that? So if you have anionic vacancies, you can see here we have A plus ion, B negative, A plus, B negative, B negative, A plus, B negative, A plus, A plus, and there should be a B negative, but here we have a vacancy. There is no atom present here. There is no atom present here. Who will tell me why is the electron present here? Why do we have the electron? Why do we have the electron here?
To make it stable.
Yeah, correct. To maintain the charge, right? To balance the charge. Here there should be B negative, but instead of that B negative we have, that is electron, which is negatively charged. Okay, so we are balancing the charge. So now this sites, here you have electron, and if you have electron and you shine light here, then what can happen? That can absorb, right? It can absorb the white light, and it can reflect a few of it back, right? It can reflect a few of it back. Now whatever it is reflecting, that will be giving it some type of color. That is why these are known as F centers. These electrons, this holes, these are known as F centers, and this is a reason why we see some type of colors in metal excess defects. Okay, the solid which are having metal excess defect, they show some color, and that is due to the F centers. Okay, so the electrons trapped in anion vacancies are known as F centers because they impart colors to the crystals. Now next is the metal excess defect due to extra cation. Again we have an extra cation, that is A plus ions, and again we have the electron that is there to balance the charge. To balance the charge, we have this electron here. Okay, we have this electron. This is how you have metal excess defect due to extra cation. Now these are very easy things because the name only suggests how the atoms will be arranged. So if you have extra cation, that will be extra cation, and you have to remember one thing, that the balancing of charge will be with electron in both the cases. In both the cases, you can see the balancing of charge is from electron. Now next is the consequence of metal excess defects. Now the consequence is very easy. You can see that if you have excess electron, that means they will conduct electricity. If the ideal crystal is a insulator, then also it is going to conduct electricity, because now you have free electrons here, because you have free electrons in both the cases. So first thing is that you will conduct electricity, and there will be color. So color with crystal with metal excess defects are generally colored. So you have sodium chloride, which is sometimes yellow, potassium is sometimes violet, and lithium chloride is sometimes pink. It is all due to the metal excess defects and due to the presence of electrons in them, due to the presence of free electron in them. We have two consequences. One is the conduction of electricity, and the next is the impartition of colors. Now we have so we have looked at the metal excess defects. Now we are going to look at the metal deficiency defects in cationic vacancies and the presence of extra anions. So here we have a metal deficiency defect due to the cation vacancy, Okay, now since we have cation vacancy, what is going to happen in the cation vacancy? You are going to have a
proton
hole. No, proton kahan se hoga? You will never have a proton. You will have a hole. Now how will you balance charge? You will balance charge by increasing the charge on cation. As you have looked, Ni2 plus was also there. and you had Ni3 plus also, है ना? So for 98, we had only 98 nickel atoms. That is why some of it was Ni2 plus, the other one Ni3 plus instead of 100 nickel, right? The ideal crystal should have 100 nickel, but we have less. That means we have deficient. The metal is deficient. So metal deficient defect due to cation vacancy. And in those vacancy, we have nothing. It is just vacant here. And then here you have A2 positive, which is balancing the charge. Is this clear? Yes or no? Please tell me. Is this clear?
Yes, sir.
Sir, please
Okay.
explain it again.
Acha. So can you see a cation vacancy? तो नाम से ये है. Yes or no?
Yes, sir.
Okay. Now, if there would be a cation here, it will be what? A positive. ठीक है?
Yes.
And all the other atoms will also be A positive. सही है?
Yes.
है ना? All the atoms. Okay. Now we don't have this A positive. Then what we can do? What we can do is we can increase the positive charge in some nearby or adjacent cation. So this is now A2 positive, right? It should have been what? A positive, but it is having this positive charge and the positive charge of this cation if it was present here also, right? So we are balancing this by increasing the charge on some nearby cation. Do you understand now why you have A2 positive? Yes or no? Tell me.
Yes.
A2 positive to balance it out. Okay. So how do we balance here? देखिए जो नाम है ना cation vacancy, it is only telling you about there is a vacancy and cation. Now when you have cation vacancy, there will be a extra negative charge. So how is that extra negative charge balanced? By adding extra positive charge. Okay. So also when you have this type of holes, they appear to be lustrous and they appear to be kind of yellowish kind, and that is why sometimes you have this cation vacancies and these metals look like gold. Okay, but they just look like gold, but they are not gold. That is why these are known as fool's gold, which is fake gold. So the positive ions may be missing from the lattice. The extra negative charge may be balanced by some nearby ion acquiring 2 positive charge instead of 1, right? That means they are acquiring larger number of positive charge instead of the like as compared to the ideal crystal. This is how you have the cation vacancies. Next is the anion vacancies. Sorry, metal deficient effect due to extra anion. So when we have extra anion, then also there will be a increase in negative charge, and that charge will also be balanced by a metal acquiring higher charge. Okay, so in both the cases you have same type of balancing consequences. Okay, here also extra anion may be occupied. The extra negative charge is balanced by the extra charge on the adjacent metal ions. Okay, is my voice breaking for everyone? Yes, Atif, is my voice breaking?
No, sir.
No. Okay. Shravi, I think it is only you. Okay, now it is fine. Great. Okay, so here we have the extra anion, and that is also balanced by a A2 positive charge. So the thing that you have to remember, so your naam hai na, you already have names here, right? You already have names here, that is anionic vacancy, and you have cationic vacancy, right? So anionic vacancy, that name suggests that there will be less number of anion, but how are they balanced? This is balanced by electron. You have extra cation, that means you will be having extra cation at interstitial sites, and how will be they balanced? By electron. Cationic vacancies, you will have less number of cation. How will be they balanced? By increasing or higher charge on nearby cation, right? And this will be also balanced in the same way if you have extra anion. So this is the balancing part which is not there in the name. Otherwise, the name is already there, right? In the name, you know what is happening, but you have to remember how it is balanced. That is more important, how it is balanced. So how are the anionic vacancies balanced? By addition of electron. How is the presence of extra cation balanced? By addition of electron. How is the cationic vacancies balanced? It is balanced by the increase in positive charge on adjacent or nearby cations. And what about the presence of extra anion? That is also balanced in the same manner. So is this clear? Yes or no? Non-stoichiometric defect, metal excess and metal deficiency defects. Yes or no? Please tell me.
Yes, sir.
Okay. Now moving on. अच्छा, एक चीज हम बताना भूल गए थे जो आपको बता देते हैं. In the stoichiometric defects, AGBR is the AGBR. Okay, AGBR is a solid which shows Schottky and Frenkel both the defects. Okay, AGBR. Okay. Now moving on. Non-stoichiometric happened. Then we have one left, which is impurity defect. Okay, which is impurity defect. For impurity defect also, you will first do this question. Please do this question. Write this question. Let me know when you are done. Write this fast now. You know when you're done. Okay, all of you have written the question. I think most of you have written the question. Okay. So now let us look at the question, what it is asking. So it is saying that NaCl is doped with this many amount of SrCl2. Okay, it is doped with this many of SrCl2. What is the concentration of cation vacancy? What is the concentration of cation vacancy? Okay, I need someone to answer me. I need someone to answer me. Okay. Now, this is, let us suppose that this is the only solid and these are the only ions that I have here. Okay, Na plus and there are Cl negatives that you are not able to see. Okay, Cl negative here, but हम Na plus को ही लेके चलते हैं. Now I want to add only one molecule of SrCl2. So when I say SrCl2, I mean Sr2 positive. Okay, I mean Sr2 positive because Cl is also there in SrCl2 and in NaCl we also have Cl only. So we are not doping Cl. Cl is not a foreign ion. Cl is the ion that is present already there. So what is the foreign ion here? What is the impurity here? It is Sr2 plus. Can all of you see that? Yes or no? Please tell me.
Yes.
Yes, sir.
Okay. Now we have this solid in which we have 4 Na positive. That means the total charge is 4 positive. Yes or no? Correct? Is that right? Yes or no? Please tell me.
Yes, sir.
Yes, sir.
Similarly, you will be having 4 negative charges due to Cl. Correct?
Yes,
Anna?
sir.
We are not changing Cl. Okay, we are not changing Cl. Cl तो वही है जो आ रहा था पहले आपका. Cl is not an impurity here. Cl is present in NaCl also and SrCl2 also. So you will not be thinking about Cl because it is not an impurity. It is not an impurity. We are not changing the number of Cl negative. That means we have 4 negative always. We have 4 negative always. Now if I put Sr2 positive here somewhere, if I put Sr2 positive, let's say I have put Sr2 positive here, then what is the total charge now? What is the total charge now? Tell me.
5.
6 positive, right?
6
Yes or no?
positive.
6 positive. Okay. Now, in order to balance it, I have to remove some sodium. In order to balance it with 4 negative, I have to remove some sodium. How many sodium will I remove?
2.
2.
2 sodium.
ठीक है, अब देखिए. Now, how many atoms do I have? I have 1, 2, 3 atoms. Yes or no? We have 2 sodium and 1 Sr2 positive.
Yes.
Right? So initially, I had 4 atoms. All of them were sodium. And after doping, we have 3 atoms. Yes or no?
Yes,
Yes
sir.
or no, guys? Tell me. Now, you tell me, if I have 3 atoms, then how many vacancy will be there? There is 1 vacancy. Yes or no? There will be 1
Yes, sir.
vacancy, right?
Yes,
There
sir.
will be 1 vacancy. Okay. Now, this is I have shown you guys how this happens, but you can also think of a formula in order to do this very algebraically. How can you do this algebraically? You can write the number of cation vacancy is equal to magnitude of, rather I should say, difference in magnitude of cationic charge. So if I see the difference in the magnitude, then you can see that you have 2 positive, right? That means the charge on Na positive, right, minus the charge on Sr2 positive. Its magnitude, that means I will just take the mod here. So you can see the what we have here +1 and here we have +2. The difference is of 1. Yes or no? Can you see that?
Yes.
Hi, Anna.
Yes,
So
sir.
number of cation vacancy for each SrCl2. If I add 1 SrCl2, then I will be getting 1 cation vacancy. So I'm adding what? So now we have to look at the number of SrCl2 doped. Number of SrCl2 doped. It is equal to 10 to the power of -3 mole percentage. Now this is very tricky sentence, right? To write. This is very tricky phrase. 10 to the power -3 mole. So 10 to the power -3 is how much? 10 into 6.022 into 10 to the power 23. Okay. And what does 68% means? 68% means 68 upon 100. Yes or no? Hai ki
Yes,
nahi?
sir.
Similarly, here also what does still mean? This percentage means this divided by 100. Is that right? Yes or no, please tell me. Sanjmaya?
Yes, sir.
If you have to get exact number, then what do you do? Just divide by 100, right? 68 upon 100. So now we have, so this will be equal to 10 to the power of minus 5 into 6.022 into 10 to the power 23, which will be equal to 6.022 into 10 to the power 18. So number of cation vacancy is also equal to 6.022 into 10 to the power 18. Is that right? Sanjmaya sabko? Yes or no? Please tell me.
Yes, sir.
Yes, sir.
Chali, please write this down. Let me know when you're done. So you now understand impurity somewhat, hai na? Now you understand impurity? Okay. Three of you are done. Raise your hand if you're done. Others also. Please raise your hand. Okay. So I think most of you are done. Okay. So there is one slide which is for the impurity defect. So you can just write this. Okay. You can just write this slide down. The impurity defect, mainly you have to keep the concept in mind that you have a different foreign atom here. Okay. Now you understand. So I can stop sharing the screen, and there is a little portion regarding the properties of solid. So let me open your OneNote, batch B, and there is 26 April. And it's Tuesday. Now, in this properties of solid, right? We have properties of solid. Now, properties of solid, it is classified into further two types that we have to study. There are two topics in properties of solid. The two topics in properties of solids are its electrical properties and its magnetic properties. Okay, so in electrical properties, we have conductors Second is insulators. And the third is semiconductors. Okay. Now, you must have heard about conductor, insulator, and semiconductor, all of these things, but we will be studying these three parts from a perspective of band theory. Now, band theory is nothing new. Band theory is just a application of molecular orbital theory, or the orbitals that we have, atomic orbital theory, you can also say. Okay. Magnetic properties also of three different types can be there in terms of magnetic properties. A solid can be paramagnetic, it can be diamagnetic, or it can be ferromagnetic. Okay. And this ferro is a new one. Para is something that you already know. All the pair, there will be some unpaired electrons. Dia will be all will be paired. In ferro, it will be highly unpaired number of electrons. So in para, it will be weakly magnetic in the presence of magnetic field. Diamagnetic are repelled in the presence of magnetic field, and ferromagnetic are magnetic even after you remove the magnetic field. So we'll learn about ferromagnetism later on. But let us first of all understand what is the band theory. Okay, let us first of all understand what is the band theory. So band theory can be explained by this image very effectively. Okay, so we have band theory. This is the topic, I can say, band theory. Okay, so generally when you have different types of orbitals and all, so you can have infinite orbitals. The only thing is there that hydrogen also has infinite number of atomic shells or orbitals, but the thing is it has only first shell which is occupied. Okay, there are other present, and that is why you can excite the electron onto further levels. That means they are already present, but these are not available, right? These are vacant, and there is no electron available there. Okay. And similarly here also, if you have a single atom, that means you can imagine that there is a 3s subshell, right? There's a 3s subshell and there is a 3p subshell. And so 3s will be lower in energy, 3s will be higher in energy, obviously. Now, if you have only one atom, then the atomic orbital will something look like this. If you have 5 atoms which are very close together, then the atomic orbital will mix and it will be looking like this, something like this. Okay. And if you have a very large number of atoms, then all this blue line, now you can imagine that there is a lot of blue lines in between also. Okay, you can imagine it like this. If you have many millions of blue lines, even if you have 1 molar, then you will have 6.022 into 10 to the power 23. That means million of different orbitals, and there will be energy levels like this. So what you are going to see essentially is a band. Rather than one single level of energy, what you will be seeing is a band. Similarly, here also you will be seeing a band of orbitals. So these are bands of orbital, and that is why the name, that is band theory. That is the name, band theory. So there are 2 bands here. So this lower level is what it is, valence band, in which you have the valence electron, and this is the conduction band. In conduction band, you don't have any electron, it is empty, it is already empty. Okay, now let us classify the solids into 3 types that we have. And those are the 3 types which are, okay, wait a second, where did it go? I had a good image here. Okay, yeah, this is not very visible. Wait a second. This is better. Yeah. Okay. So here you have insulator, semiconductor, and conductor. As you can see, in insulator, the band gap, that means the gap between the valence and the conduction band, is very. Now, if it is very high, then even if you supply some kind of energy, this energy is not enough to excite the electron to the conduction band, and that is why there is no movement. In semiconductor, if you have, let us suppose, 10 electrons, then what will happen? The electron, it will go to the conduction band, there will be only 2 or 3 electrons which are going to the conduction band. That means it is the conductivity is low here. And in conductors, what happens? You have overlapping of the band gap. Okay, so you have overlapping. The conduction band and valence band, these are overlapping with each other. So this is the theory of band theory. Simple theory it is. You have bands. How do we have bands? Due to atomic orbitals. And if you have many atomic orbitals, they will be looking like a band. And if you have a gap between the valence and the conduction band, which is very high, that is known as insulator. If you have a solid in which the band gap is low, that means you have a semiconductor and in which you have overlapping here. Here you are having overlapping. And if the conduction band and the valence band is overlapping with each other, that means you have a what? You have a conductor. You have a conductor. Okay. So is this clear? So if you see the insulator, the band gap is generally of 6 electron volts. And in semiconductors, the band gap is of 1 electron volt. And usually conductors, they have overlapping with each other. That is why you don't have any band gap here. So you neither have to study insulator in detail, nor you have to study conductor in detail, but you have to study semiconductors in detail. And how can we make semiconductors more efficient, and how can we conduct more electricity through semiconductors? Now this is the position. What we can do with semiconductors. So we know that in conduction, we know that the conductivity is due to free electrons. Yes or no? It is due to free electrons, correct? If you have free electrons, then only what you can do? You can have electricity. There can be conductance only if you have free electrons. Is that right? Yes or no? Please tell me. Are hi, Anna. Yes, na? What happened? Atif, Khalil, Minashi, Shravya. Electrical conductivity can be only there if you have free electrons. Yes or no?
Yes, sir.
Anna? Okay, fine. So in semiconductors, what we can do? In semiconductors, we can add some free electrons. We will do something, and that will lead to addition of free electrons. So for that, look at this picture here. Wait a second. So mainly semiconductors are group 14 elements. Okay, semiconductors, these are group 14 elements, and we have taken one example which is of silicon. Now this silicon atoms, here we have silicon atoms, all are bonded with each other, right? All are bonded with each other, and each silicon has 4 atoms, right? Each silicon has 4 atoms, right? So you can imagine that one of this silicon, it has this atom is, this is the red atom here, and it has 1, 2, 3, 4. These are silicon atoms. Then you have this green one. So green one has 1, 2, let us say 3 and 4. These are the green atoms which are of silicon. Then again you have this red atom. So this red atom is their electron is 1, 2, 3 and 4, let us say. And similarly you will have another green atom here which has its electron is here 1 and say 2, 3 and 4, right? So these are the electrons of silicon, right, in each of them. Now there must be one atom here whose electron will be this side. So yeah, imagine this is an array of silicon atoms, right? It conducts electricity, but the conductance is not very high. So we can do something. We can replace silicon, and instead of silicon, we will add some other material. Now, what other material can we add? So it is very easy. You have 14, and then after 14, you have group 15. So 14 will have only 4 valence electron. 15 will have 5 valence electron. Now, when I dope this with phosphorus, as you can see, there is a valence electron which is extra here. That is this electron. Can you see this? Yes or no? Please tell me. This
Yes.
electron, 5th electron is extra. Now, when you have extra electron, then what is going to be there? Conductivity will increase, right? Conductivity will increase. Now tell me what is this is having extra electron. Extra electron. Wait a second. Yeah. So if it is having an extra electron, then what will be the charge? Tell me. What is the charge, positive or negative, for electron? What is the charge for
Negative.
negative? That is why these are known as negative n-type semiconductor. Okay. So when you dope a group 14 element with one of the group 15 elements, then you get n-type semiconductor. Is this working clear? Yes or no for n-type semiconductor?
Yes.
ठीक है, देखिए आप ऐसे ध्यान रखिएगा all of you कि group 14 is semiconductors. Group 14 is semiconductor. ठीक है. then what you can do, you can add electrons. If you are adding electrons, then you have to move towards more, like 14 ke baad 15. So 15 you will have n type. If they ask how will you create n type, then you will remember n type is negative. That means more electrons. More electrons mean I have to have more electrons than 14. So 14 ke baad 15. Now this is p. P type में क्या होता है? Let me also tell you. P type में proton नहीं होता, ठीक है? There is no proton. What you do with boron? Boron is what now? 13, group 13 element. Yes or no? Boron is group 13 element. A group 13 element will have only how many electrons? It will have only 3 electrons, and that is why you will have a hole here. Can you see this hole? The white. Yes or no? Tell me.
Yes, sir.
Now, what is happening to the hole? Now, when I put electricity here, this electron can move here. Now, there will be a hole this side. Now, then what will happen? The adjacent electron will move and there will be a hole here. The adjacent electron will move and then there will be a hole here. So the movement I have facilitated. And main thing is what? There should be movement of electrons, right? There should be movement of electrons. And that movement of electrons can also be present by creating holes. If you create hole, then the nearby electron, it can move. Then you have a new hole, like not a new hole, but a hole in a new position. Then another electron moves and there is a hole in a new position. Then another electron moves. So what is there? You are seeing a movement of electrons and also you are seeing a movement of holes. The hole is also moving. And if you have the hole, you have, let us suppose that you have this hole C and there is negative, 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 and one thing is vacant here. Now, in a sea of negative, a hole will act as a positive. Okay. In a sea of negative, a hole will act as a positive. You can also imagine it like this. You have a colony in which everyone is millionaire, and there is, in which, let us say, everyone is billionaire, and there is one army who is millionaire. So he will feel like a poor person there also, right? Similarly, if you have a sea of electron, a hole in a sea of electron will feel like a positive charge, and that is why these are known as p-type semiconductors. Is that clear? Yes or no? Please tell me. Is this
Yes,
clear?
sir.
Why is it known as p-type semiconductors? Yes or no? G.
Yes, sir.
Everyone. Okay. So this is the completion of your solid state chapter. Okay. This is the completion of solid state chapter. Now I'm giving you guys the imperfection in solid, then new PPT. Okay, wait a second. Let me stop sharing the screen. ठीक है. And wait a second. वो तो बताया नहीं आप लोगों को हमने. एक चीज तो बच गया ना, magnetic properties. Paramagnetic, diamagnetic, you already know. Para will be paired, para will be unpaired, dia will be paired. Ferromagnetism is a new word here. Okay, so let me tell you guys what is ferromagnetism. Simply speaking, ferromagnetism are the objects that act as magnet. Okay, or an object that you can make magnet from. Okay, so these are objects from which you can make magnets. Okay, from which you can make magnets. For example, iron. Iron can be magnetized and it can be made magnet. So in ferromagnetism, what happens? The magnetic dipole moment is present even after removal of magnetic field. Okay, a little example I can give you guys. All of you have played with magnet, yes or no? All of you have played with magnet, right? Nahin?
Yes, sir.
Anna. So if you see, if you stick a, let us suppose this is a magnet here, and you are sticking a small, what you can say. Let us suppose that you are sticking a small coin here. Okay. Now this coin can also stick further coins, yes or no? Now this coin can also
Yes,
act
sir.
as magnet, right? So this is how you give magnetic moment. Now we have very small magnet. That is why if you have a coin, even if it is made of iron or something, and it get magnetized for a while, if you remove it, then the magnetic dipole also is removed. But if you have a very high or strong magnetic field, and if you keep the iron or something there, then it can be magnetized. Okay, so these are the ferromagnetism. This is ferromagnetism, in which you have no pair of electrons. There is none paired electrons. All of these are unpaired electrons. Okay, in this ferromagnetism, we have all unpaired electrons in ferromagnetism. Okay, and that is why when we remove the magnetic field, then also you get some dipole moment. Okay, so these three things, that is conductor, insulator, semiconductor, paramagnetic, diamagnetic, and ferromagnetic, you will write from